Hello everyone, this video covers section 4.2, Richardson Extrapolation. So the idea of extrapolation is that we're going to use the exact same methods from 4.1. We're going to extrapolate, and I'll explain what that means with some examples to increase the accuracy of the method. And by accuracy, I mean this. Recall from section 4.1, the first method we use, the forward difference or backward difference, was equals to this. Okay. Minus f prime of x0 h over 2, then the second derivative, and it keeps going forever. Remember that we decided to stop it here, and this is what we call the error bound, and we use the Cassie notation since we stopped there. But in essence, you can say that f prime is equals to f of x0 plus h minus f of x0 over h, and then plus or minus, but you're going to say plus o h. Actually, it should be big O of h, which means that this is the error, and the rest doesn't matter. So this is the dominant error. That's why that's the error bound. So what we want to do here is, obviously this is smaller than this one, so we're gonna do algebra, really algebra. So you get rid of this one, and we will end up with h squared instead of h, because remember, O of h squared is better than O of h. So the goal of this section is to use the same methods we have, the forward or backward differences, the midpoint formula, and to increase the accuracy. So to go from h to h squared, or h squared to h to the 4, and so forth. And all it will require is just some algebra. Now the notation is a little confusing at the beginning, but you technically already know what this means. So this is the notation, and we just call it M for lack of a better name for the extrapolation. But notice the method we're going to use is going to be called M1H. So if we use a forward differences, this will be M1. If we use the midpoint formula, that will be M1. And then here K1 through Kn, it should be K3, are just constants, and this H relates to this H squared relates to that one, and so forth. So this is the generic way to write the notation. So in a shorthand notation, that means that M implies that M is approximately equals to M1 of H plus O of H if we have this expansion, this and this is the same thing. Again, we're going to do some algebra right now. The goal is to change from H to H squared. And I mentioned this a few times already, but let me tell you one more time. This M1H depends 100% on the method you are using. Either this, the forward or backwards, or the midpoint formula, or any of the methods from 4.1. Alright, so for lack of a better name, let's call this equation number 1. So what we want to do is in equation number 1, so we're going to replace h by h over 2. So technically, we're going to divide the step size in half. And notice that if we have this, if you change h by h over 2, we will get this part. So this corresponds to this corresponds to this, and so forth. Now, notice that this is a function of h over 2. Well, this is multiplication, okay? So just be careful with that. So therefore, from here, this implies that m is equals to n1 of h over 2 plus k1 times h over 2 plus k2 h squared over 4 k3 h cubed over 8 and so forth. Then if we multiply that by 2, 2n will give you 2 and 1 h over 2 plus k1h plus k2h squared over 2 k3h cubed over 4 and so forth. And let's call now this one equation number 2. Now if we do equation 2 minus equation 1, we get that m is equals to 2 n1 of h over 2 minus n1 of h plus k2 of h squared over 2 minus h squared. We're just combining line terms. Then plus k3 h cubed over 4 minus h cubed, and then it keeps going. Right, so therefore the value for m is going to be 2 n1 of h over 2 minus n1 of h minus k2 h squared over 2 once you combine the like terms, and then minus 3 over 4 k3 h cubed, and then that. Now we're just gonna rewrite this part. Notice here you have 2 and 1, so we're just going to expand it. This is the same thing as n1 of h over 2 plus n1 of h over 2 minus n1 of h. So therefore here we just rewrite it. So this will give you this match. You'll see why this is going to be very important later. And then this is minus k2h2 over 4 k3hq minus, and then it keeps going. Then usually you combine these two, and all of this part, all of this is now going to be called n2. So it will be n2 of h. So the red part becomes that. And notice that now n2, the error bound increase from h to h squared, which was the goal. So notice the truncation error now is h squared, which means this one is, you can rewrite it as n2h plus big O of h squared, which should be more accurate than n1. All right, for the next example we're going to do is the same function we did before. So remember from last time, the example we have was that f of x was equals to 2 cosine 2x minus x. And last time we approximated that f prime of minus 0.3 was equals to 0.914. So therefore this implies that n1 of 0.1, because that was the value for h. Remember, h was equals to 0.1, x0 was equals to minus 0.3. That this is equals to 0.914. So that's what we did last time. And also last time we have that the exact solution for f prime of minus 0.3 was equals to 1.25856. So now we're going to use this information to find n2. All right, so remember that in the previous example, the value for h is 0.1, so that's not going to change. But now we're going to need to find n1 of 0.05. Why? Because h divided by 2 is going to be 0.05. Remember, this is the same thing as finding f prime of negative 0.3 by using 0.05 instead. So this should be equals to f of minus 0.3 plus 0.05 minus f of minus 0.3, everything divided by 0.05. This is the new h now. And once you simplify everything, you should check this by yourself. Stop the video and do all the computation. It should be 1.0892. All right, so don't forget that this is the same thing as n1. This is n1 of h over 2. So now we need to find n2. So we're going to use this formula. And we found this already. And this is the same value from the last section. All right, so therefore n2 of h, which is what we want to find now, is n2 of 0.1. Remember, the value for h is still 0.1. h over 2 is the one that is 0.05. So this is the same thing as n1 of 0.05, which we just found, plus n1 of 0.05 minus n of 0.1, which is equals to 1.0892 plus 1.0892 minus 0.914, and this simplifies to 1.2644. Notice that this is very close to the exact solution, or definitely closer than n1. So the exact solution was f prime of minus 0.3 is equals to 1.25856. So you can see that this is way closer to this than this was. So that's the advantage of the extrapolation. So you're still using the same method. You had to do more work, but it's still the same method. You just improve the method. All right, you didn't get that one. Here's a chance to redeem your sins. Let's do a different one. Now let's say that you have a new method. Okay, so this is a new method, which could be the midpoint formula or another formula that uses 3 points. So it's another formula to find derivative. So a new method to find f prime of x0. Okay. And let's say that this is the Taylor expansion for the method, or one of the expansions. Notice that this one, unlike the previous one, this one is square x to the 4, h to square, h to the 4, h to the 6, and so forth. So therefore this one is already O of h squared. So when we do the interpolation, we want to get rid of this one so that we end up with h to the 4. So the algebra is the same as the previous one. So here we're going to have m is equals to n1 of h over 2 plus h squared over 4 times k1 plus h to the 4 over 16 times k2, and then plus h to the 6 over 64 k3 and so forth. All right, so if we multiply m by 4, we will get the following. We'll have 4 and 1 of h over 2 plus h squared k1 h to the 4 over 4 K2, and then h to the 6 over 16 K3. Now let's call this equation star and this equation triangle. So again, if we do equation triangle minus the original equation, we get the following, that 3m is equals to 4 and 1 h over 2 minus n1 h minus 3k squared h to the 4 over 4, and then minus k3h to the 6, and this will be times 15 over 16. That's just algebra, so make sure you check that. Now notice that now this one, the order is h to the 4 instead of h squared. Now you just had to rewrite it in a nice way. Alright, so from here we have that m is equals to 4 over 3 and 1 of h over 2 minus n1 h over 3, then minus k2 h to the 4 over 4, and minus k3 h to the 6 times 5/16 plus that, which you can rewrite it as n1 of h over 2 plus, then you factor the 1/3. This will be n1 of h over 2 minus n1 of h, and then the same thing, 5/16 k3 h to the 6. Alright, so here notice that the 4 over 3, this is just basic arithmetic, is equals to this plus that. Okay, so 1/3 plus 1 is equals to 4/4. You're just rearranging the answer, and all of this is what we're going to call n2 of h, just like we did in the previous one. So therefore from here, this implies that m is going to be equals to n2 of h minus k squared over 4 times h to the 4 minus 5/16 h to the 6 times q3, and then minus or plus, actually doesn't matter, and that will be the new formula. Okay, remember from last class, okay, last class we have a method that it was OH squared, which was the midpoint. So remember, f prime of x0 is equals to 1 over 2h, and this was f of x0 plus h minus f of x0 minus h, and then the error bound was equals to this. This was on actually C, and but if you don't step in C, this keeps going. So this will be x0 and then minus that. But the point is that this one was O of h squared. So therefore that means we can use this. Okay, so remember this was called the midpoint. Midpoint formula. And also from last time, we approximated f prime of minus 0.2, and this was around 0.547. But remember that this means n1 of 0.1, so h is still equals to 0.1. So to complete the interpolation, we're gonna need to find, so we still need n1 of 0.05, because h has to be divided by by 2. So we will do that in the next page. Right, so remember that we're using the midpoint formula, which is the following. 1 over 2h f of x 0 plus h minus f of x 0 minus h. Okay, so that's what we're using. For the example we're going to do right now, x0 is equals to minus 0.2. The value for h is 0.1. And we already know that n1 of 0.1 was equals to 0.547. And don't forget that the function we are using is 2 cosine 2x minus x. Okay, so we still need to figure out n1 of 0.05, which should be equals to f prime of minus 0.2 if we use this new value of h when h is now 0.05, and we plug it into this equation. Okay, so therefore this implies f prime of minus 0.2 will be 1 over 2 times 0.05 times f of minus 0.15 minus f of minus 0.25. And once you simplify all of this, again, you should stop the video and check that this is the case. This is 0.55, 50, 80. I believe this value is 2.060673, and this one is at 2.005165. All right, so therefore n2, using this formula, so from here we have the n2 of h, which in our case is n2 of 0.1. This should equals to n1 of 0.05 plus 1/3 of n1 of 0.05 minus n1 of 0.1. And now we have all these values. So this should equals to 0.55, 50, 80 plus 1/3 times 0.55, 50, 80 minus 0.547. And all of this equals to 0.55777. Again, just should stop the video and check. Now the exact solution for f prime of minus 0.2 is equals to 0.55, 76, 73. So you can see that the answer is pretty close. Remember that f prime is equals to minus 4 sine of 2x minus 1, and then make sure you use radians, and that's it. Now there is nothing special about stopping in n2. You can actually keep going. So for example, if m, the last m we got, was equals to this, n to h minus k2 of h to the 4 over 4 minus k3 times 5/16 h to the 6, so 4, we can do the same thing and find n3. And by finding n3, now this will disappear, so this will be O h to the 6. Okay, the idea is the same. You still want to replace now the new h by h over 2, which compared to the original one, it should be h over 4. So then from here we will have now m equals to n2 of h over 2 minus k2 over 4 times h to the 4 over 16, and then minus 5k3 over 16 times h to the 6 over 64 minus that. Now, if you do the same algebra we did, you will end up with something like this, and you should check this. This is one of the homework questions, and it's very likely you'll have something like this on the test too. You will end up with 16 n2 of h over 2 minus n2 of h, and you can still rewrite this. The point is that the h to the 4 will be gone now, and you will end up with k3 over 64, and now this will be h to the 6, and this will keep going, but the point is that now this one is oh to the 6. So technically you can say that n1 was, for this particular one, n1 was oh squared, n2 will be h to the 4, n3 will be oh to the 6, and so forth. Okay, and that's it. And this is what we call Richardson extrapolation. So just to be clear, this part now is going to be called n3 of h. So therefore you can say that now the new m is equals to n3 of h plus or minus big O h to the 6. And now we are done.